So welcome everyone. I am Aurélien Belès, one of the organizers of this Federated Learning Word seminar, along with Peter Richterick, Virginia Smith, Dan Alistair, and Samuel Horvat. So the goal of the seminar is to provide essentially an online forum to discuss the latest scientific results in all aspects of federated learning. So this includes distributed optimizations, learning theory, privacy, security, personalization, things related to communication compression, and of course, aspects related to systems, hardware, and also applications. So before I introduce today's speaker, maybe just a quick recap for people who might not be familiar with how we handle questions. So during the talk, all the mics are off by default for the audience, but you should feel free to use the raise hand features. So that's in the participants menu. And or write question in the chat, and we can ask the question for you, or we can turn your mic on, so you can ask question yourself. So Vitaly has agreed for people to ask questions during the talk, so please feel free to do that, and we will keep an eye on any questions. All right, so our speaker today is Vitaly Feldman. Thanks a lot again for accepting our invite. So Vitaly is a research scientist at AI Research. He holds a PhD from Harvard, where he was advised by Leslie Valiant. And he was previously a research scientist at Google Brain and IBM Research. Vitaly is working on theoretical foundations of machine learning and privacy-preserving data analysis. So he's got recent research on generalization and links with memorization in machine learning, work on distributed privacy-preserving learning and privacy-preserving optimization. He was the co-organizer of the Simons Institute program on data privacy in 2019, and this year he received the Caspar Boden Award for outstanding research in privacy-enhancing technologies for his TOC 2020 paper on those links between learning and memorization. And I think that was making him the fourth Vitaly to win this award, right? And I checked, I think you're the first Vitaly to give a talk at Flow. So it looks like we need to invite more Vitalys. So today, Vitaly will talk about some work on privacy amplification by shuffling. So this essentially allows to improve upon the local differential privacy guarantees by applying random shuffling of data points. So this is closely related, but not equivalent. I suspect maybe Vitaly will explain a bit this to the shuffle model of privacy, which is a useful intermediate point between the local and central models of DP. And so Vitaly will explain how nearly optimal amplification guarantees can be obtained from an arguably simpler analysis compared to previous work, and discuss a bit implications of these results for private estimation and learning. So again, thanks a lot, and Vitaly, welcome, and the floor is yours.
Thank you for the kind introduction, Aurélien, and the invitation. Indeed, I hope I won't be the last Vitaly giving a talk in this seminar. So yes, I'm going to talk about the shuffle model and the privacy guarantees of privacy amplification in this model. It's joint work with my two wonderful colleagues, Audra McMillan and Kunal Talvar. I should also briefly mention that the opinions in this talk are my own, don't represent my employer. So the basic framework we're looking at is the standard one, which I don't think needs introduction. In this seminar is that of federated data analysis, in which we have clients, each holding some data, and we'll denote this typically by X1 through Xn. And we'll have a server which wants to perform some kind of data analysis on the data held by the client devices, such as building histograms or training machine learning models. And with this purpose, the server can communicate with the clients. Of course, it's as it is often the case in practice, the data residing on clients can be sensitive. And in this case, we need to guarantee some kind of, we need to provide some kind of privacy guarantees to the clients. And as sort of I could say at this point, a classical approach to doing this, one that dates back to work in social sciences by Warner, and more recently done in the context of differential privacy, is this notion of differentially private local randomizers, which basically asks that each client runs a differentially private algorithm on their own data, and then sends that differentially private randomized output to the server. Specifically, this the guarantees that this gives is that the distribution for any two different inputs, for any two possible values of the data that the user might hold, the output distributions that will be observed by the server are close, and closeness is measured using the standard differential privacy parameters, which will be in this particular, which was usually denoted by epsilon. And I'll assume that you're roughly familiar with all these notions, but I'll briefly recap them at some point. So, so this is a very it's a very nice model. It's requires relatively little trust from the users. Basically, the user is locally randomizing their data, and in fact, it has been, as we all know, has been deployed in industry. So, so it's in many ways a very attractive solution, which is kind of relatively easy to verify and deploy, but it has disadvantages. Basically, the disadvantage is that the best achievable accuracy in this model is relatively not so great. For example, looking at the problem of estimating just the mean of values, say in 0, 1, the best achievable error in this case is roughly 1 over epsilon square root of n, even though if we were to trust the server with the data and only require the central notion of differential privacy. So basically, we would only require that the output by the server satisfy the epsilon differential privacy, and not not the local model. Then we could achieve error of on the order of 1 over epsilon n, which, as you can see, is better by a square root n factor, and that's of course a very significant factor in practice. So one way to sort of address this discrepancy was first proposed by Vitaly and al., which kind of adds anonymity into this picture. And specifically, it adds a component which is called a shuffler that basically receives all the inputs from the clients, strips them from any sort of identifying information and timestamps, basically shuffles them completely randomly and uniformly, and then sends the output, the shuffled output to the server. And in this case, we basically the shuffler does not cannot see anything about the data. We don't really need to trust the shuffler because whatever the data, both the data that is sent and comes out is encrypted by a key which is known, say, to the server. So as long as sort of the server and the shuffle do not collude, we will sort of get the benefit, the user's data gets the benefit of an anonymity. Basically, the server does not know which of the sort of the communications comes from which client, and that intuitively adds privacy because I mean, now in addition to being randomized, the user reports are mixed in with some other randomized reports, so it should be telling us less about each individual user. But it's potentially not so simple to capture this privacy implication. Indeed, Vitaly and who introduced this model did not give any guarantees for this model. And the first, and the question is, can you sort of provide some kind of guarantees? Specifically, if we think of each user as sending their report with epsilon naught differential privacy, we can ask what kind of guarantees can we provide on the outputs from the shuffler. What kind of privacy guarantees hold if all that one can observe is this output after shuffling. So the first formal analysis of this model came in 2 works in 2019, which were in fact concurrent. The first one by Cho and others, they have analyzed privacy amplification for a specific local randomizer referred to as binary randomized response. This is basically a mechanism which reports on just 1 bit by flipping it with some probability randomly, and I'll describe it in more detail later. And for this specific mechanism, they showed that if you randomize with these reports with epsilon naught, then the shuffled output will have the following privacy guarantees. They will be in the epsilon delta notion with some delta. And the epsilon has this form. It's a little harder, maybe it might be a little hard to understand at first sight, but ignoring this log factor, it's much easier to understand if we split it into regimes where epsilon naught is less than 1, then this bound is roughly epsilon naught over square root of n. Basically, as you can see, we're amplifying the privacy by roughly square root n. Of course, we are losing this square root of log 1 over delta, but it's typically smaller. And for epsilon naught, which is greater than 1, we get something like e to the epsilon naught over 2 divided by square root of n. So we still get the square root of n, but now we are amplifying from actually a higher value of e to the epsilon naught over 2. So that's the guarantee that one gets for a binary randomized response. And the other work which gave analysis for
let me interrupt
yes.
with a question from
yes.
Konstantin.
Thank you. Sorry, when you mentioned the variance for estimator a couple slides ago, I am familiar that this bound with 1 divided by, so the second bound is fine for additive Laplacian noise. But I'm curious, can this bound be improved with another like additive noise with another PDF? Or this bound is tight?
No, this bound is tight, and that's why I put kind of this theta is basically upper and lower bound for epsilons less than 1 to be more accurate. But that's for especially for the so they both bounds can be better with epsilon which is larger than 1, but for epsilon smaller than 1, that's the tight bound.
Thank you.
For both bounds. So the second work which analyzed this model is the work by Erling Son and others, including myself and my co-author Kunal, where we basically give a general privacy amplification result via shuffling, and I'll describe that in more detail just a bit later, and which basically applies to arbitrary randomizers. And it gives the following bound on the shuffling privacy parameter after shuffling, which is very similar to the one I just described, except the exponent here is, instead of being e to the epsilon over 2, the exponent is e to the 3 epsilon 0. So if we look at the two different regimes, in the regime where epsilon 0 is less than 1, we get the same dependence, simplification by square root of n factor. But in the regime where epsilon 0 is greater than 1, we get a noticeably worse bound of e to the 3 epsilon 0 divided by square root of n. And that's since this regime where epsilon 0 is larger than 1 is practically important and useful, this bound is effectively much worse in this regime. So basically the situation, yes?
Yeah, we got another question.
Please.
Sorry for interruption. So I was just wondering if, in the previous slide, if we have delta not necessarily 0 for local differential privacy, can we get a better error rate for the mean estimation problem for the previous slide?
So no, these ones are tight even with delta, and we will talk a little bit about delta. For local randomizer, delta basically doesn't help. For central, in this case, for central it does help, but not for this simple problem. Like if once we go to higher dimensions, for example, if we're doing d-dimensional mean estimation, then we would see a difference between epsilon and epsilon delta. But for this particular problem, there is no delta, doesn't even play a role. And we will discuss a little bit delta for some of the results a bit later.
Okay, thank you.
All right, so the situation we end up with these two results is that we have this very special case, but the analysis is very simple, and actually it's known to be tight. It's kind of actually pretty easy to verify that it gives the tight analysis of application for this by privacy. And the second result, which is very general, but it's at the same time quite involved. It's not a simple proof, and it's not a tight bound. So we are kind of, we're not in a great situation. And the hope of sort of the plan in this work is to address the situation. But before going forward, let me describe in a little bit more detail is what is this general privacy amplification via shuffling that I've described. And the formal statement of this theorem is the following: is that for any adaptive sequence of epsilon-0 differentially private local randomizers, A1 through AN, and adaptive here means that actually it's a sequence, and the output the output A2 can depend on the observed output of A1. And so, and basically for any randomizer, it's can also take as an input the output of all the previous randomizers. So it's a sequence that can depend on previous results. So for any such sequence of n potentially different randomizers, and data set X, which is X1 through Xn, will denote by this A subscript shuffle of X be the algorithm which does the following. First, it shuffles all the inputs via random permutation, and then applies these local randomizers in sequence. And again, it's an adaptive sequence, can take the previous outputs as inputs to the next randomizers. So we define the algorithm in this way. And then for this algorithm, we have the following guarantee is that this algorithm satisfies differential privacy with the parameter that I've described. So that's the bound. It might look a little strange because here in this statements of the result, we are actually shuffling the inputs to the randomizers and not the outputs. But one kind of very simple observation is that if all the randomizers are identical and non-adaptive, they're fixed. If you just use a single fixed randomizer for every single user, then it doesn't matter whether you shuffle the inputs before or after, because it's still, you apply the same thing and basically it doesn't matter. So in this case where all AIs are identical, it implies privacy amplification with shuffling, which is the one which is typically used in the shuffle model that I've just described. But at the same time, this kind of more general formulation has the advantage that it allows one to also analyze interactive algorithms like differentially private stochastic gradient descent. And in those algorithms, as you all know, we compute gradients on points that have been output by the previous iterations. And as a result, effectively, the randomizer at each step is kind of this adaptive because it takes the output of previous randomizers and then computes gradients and then applies randomization on that one. So this more general version allows one to also apply the analysis to stochastic gradient descent and interactive algorithms more generally that are not allowed by the non-adaptive simpler analysis. So in a way where kind of it is in some sense a more general result, it just shows that just shuffling the inputs amplifies the privacy of arbitrary locally differentially private algorithm, the algorithm which has guarantees with respect to every single input. So that's the result. Now let me briefly mention some more related follow-up prior work. Sorry, some more prior work. So another very interesting and result I very much like about privacy amplification by shuffling was given by Bal and others, who show that for the general, well, basically any fixed randomizer can be used, but in a non-adaptive way. They give a bound which is, again, looks like the previous bound, but now the exponent e to the epsilon 0. So it is better, it is more constrained, but it is does give a tighter bound. They also give a way to numerically compute the bounds, which is quite a bit tighter than a theoretical analysis, which is also important for applications. The second result I want to mention is that the Bal and others have also found a way to slightly sharpen the general analysis from the Erlingsson and others' work that I've mentioned, and shave the constant from 3 epsilon 0 to 2.5 epsilon 0. I mean, but it is essentially the same analysis, actually even a more complicated analysis, and it is still not tight. And finally, the people have also, one can kind of relatively easily get an extension of these results to the case where randomizers satisfy epsilon naught delta naught differential privacy by first converting the LDP each randomizer, which is epsilon naught delta naught, into epsilon naught randomizer, which is close to it. But using this kind of standard transformation incurs kind of additional constant factor in epsilon 0. And if you do it kind of in this kind of black box way, which you will get a really bad dependence of e to the 20 epsilon 0, which is completely impractical. So basically, even though there has been quite a bit of some nice follow-up work, we're still in this situation where all we have is relatively involved proofs, and we don't have tight bounds. So let me now describe what we give in this work. And in this work, we give the bound, which is basically tight up to constant. It has the same bound as we had in the for the binary randomized response with e to the epsilon over 2. And it is tight up to constant. It's relatively easy to show. We have the results have other advantages. For example, we give better bounds for specific local randomizers by giving sort of another version of the proof, which can exploit additional structure in the randomizer. And in particular, we get better bounds for some specific randomizer, like carry randomized response. We also show that our result extends to epsilon delta differential privacy, local differential privacy, with almost no loss. We still get exactly the same e to the epsilon naught over 2. We do, of course, pay some like n times e to the epsilon times delta 0 in the additional delta parameter. This part, I don't know how optimal it is, but at least there is no price in epsilon 0 independence in the epsilon parameter. Another advantage of our result is that it's easy to compute numerically and get actually significantly tighter bounds that one can get sort of in via closed form expression. This again is very useful for applications. And specifically what we show, and I'll explain this later, is that our result is actually a reduction of the question of this bound to a divergence between two specific explicit trinomial distributions. And then, which means that you can sort of just take and compute whatever divergence you're interested in. You can just plug this pair of distributions and compute the divergence, and whatever the bound you'll get is actually applies to arbitrary randomizers. So basically gives you a bound for all for the entire for arbitrarily complex scenario. So since I mentioned the numerical bounds, let me compare the numerical results that we get out of this work with some prior work. So first of all, this plot uses n, which is about 1 million, and delta of 1 in 1 million. And we plot the dependence, we map from epsilon naught, the bound, the parameter of the local randomizer, to epsilon that went down as a result in the bound. And it's kind of basically it's a log-log plot, except for when epsilon is larger than 1, it becomes 1-to-1 plot, which is kind of a natural way to represent this dependence on these parameters. So in this plot, the lower is better. So the better parameter epsilon we get is better. And the lowest line in this plot is the green line, which is actually the lower bound. This is the best. This is a bound which is computed numerically for amplification of binary randomized response, and it's actually a lower bound. One cannot get better bounds than this green line. The next line is the purple line. Is the result of the upper bound that one gets from our work when this bound is computed numerically. And as you can see, it's typically within a factor 2 of the best possible result, which is the lower bound for binary randomized response. The next line is this dashed line, dashed brown line, and it actually is the closed form bounds for the binary randomized response from the work of Chu et al. Just above it is the closed form expression which we give in our work. We basically show that our closed form expression is almost as good as the best known closed form expression for binary randomized response. And then we have 2 more bounds in the prior work. One, the blue line, is the result of Vitaly et al., this privacy blanket paper that I guess maybe not as general, but it has this e to the epsilon 0 bound, and it's computed numerically. And finally, the red dashed line is also a closed form expression from the work of Vitaly et al. That sort of sharpens the closed form expression, and it applies to the most general form. And as you can see, both of those bounds for more general mechanisms are quite a bit worse, especially for larger epsilons. Once you go past epsilon equal to say 1, the difference bound is orders of magnitude. So also, as I mentioned, this is for epsilon delta. One can also compute other divergences since using our reduction. And specifically, we also looked at the numerical evaluation for Rényi divergence. And the advantages of using Rényi divergence is that it's much better for composition. Basically, if one is planning to use many applications of this algorithm, not just once, it's much better to compute the guarantees in terms of Rényi divergence, compose, and then maybe convert to epsilon delta. And it's not so important what Rényi is, but it just looks at Rényi divergence of certain order alpha instead of the sort of this infinity divergence, which is the standard notion of differential privacy. And here we map for a specific setting of n and epsilon, n equals to whatever this 100,000 and epsilon equals to 5. We compare our work, we compute for different moments, for different values of Rényi moment, the epsilon that one gets, the divergence that one gets for this value. And here again, the lowest line is the lower bound, again computed numerically, the best one could possibly hope for, computed for the binary randomized response. This pink line just above it is the bound that we get. The dotted line is sort of the epsilon naught, is basically no amplification. And finally, we also compare with there isn't that much to compare with. We are comparing with a follow-up work by Girgis and others who have basically used a very similar idea, but kind of in a weaker form, and try to also compute the more closed form expression for the sort of maybe produce somewhat easier to compute bound than, but the resulting bound is actually a lot worse. So it's again, it's not very useful given the bounds that we can compute from our reduction. So that's all that I want to say, kind of in terms of the high level properties of the results. Now I'm actually ready to go and tell you a little bit about the proof. And as I promised, the main advantage of in my mind, of this result is actually this relative simplicity of the proof. Everything is relative, but I do believe that our new proof in some ways demystifies the privacy amplification by shuffling, kind of in making it kind of much more understandable in what is actually going on. Why does it hold? So before we go to the proof of them, to the full proof, let me start with a warm-up case, which is proving the bound for binary randomized response. It's indeed a very simple result, and there are actually very easy ways to derive it. But let me review it, because in a maybe somewhat different way, since I'll be building on this warm-up to show our general result. So first of all, what is the binary randomized response with parameter epsilon naught? It's a randomizer, well, denoted by R, which receives a bit as an input, and bit B, and outputs B with probability e to the epsilon naught divided by e to the epsilon naught plus 1, and outputs the negation, the opposite value, with probability 1 over e to the epsilon naught plus 1. It's easy to see that it satisfies epsilon 0 differential privacy. An alternative and equivalent way to describe the same mechanism is to think of it as outputting B with probability e to the epsilon 0 minus 1 divided by e to the epsilon 0 plus 1, and then 0 with probability 1 e to the epsilon 0 plus 1, and 1 with probability 1 over e to the epsilon plus 1, which is, again, can be equivalently seen with, we're just, again, redistributing the outcomes a little differently. An equivalent way to see that is that R of B outputs the input with probability e to the epsilon 0 minus 1 divided by e to the epsilon 0 plus 1, and outputs a random coin flip with probability 2 over e to the epsilon 0 plus 1. Hope that makes sense. We're just thinking of this mechanism as first kind of deciding with some probability what it's going to do, whether it will output its original value or output a coin flip. And then, of course, if it chooses to output a coin flip, then it flips the random unbiased independent coin and outputs that value. And it's just an equivalent description of the same algorithm. So now let's look at two data sets, and we'll, for simplicity, assume, I mean, without loss of generality, that they differ in the first element. The first data set has first element equal to 0, and the second data set has first element equal to 1. Now, one thing which is very easy to observe with binary randomized response, because the outputs are just always 0 or 1 and they're shuffled, the distribution is completely determined by the number of ones, because again, it's after shuffling, it's symmetric. So the number of ones completely outputs describes the distribution. The distribution over the number of ones describes the output distribution completely. So let's now think of this distribution over ones, and it is not hard to see that it can be this distribution over shuffle, or after shuffling, this distribution on the number of ones can be generated in the following. A random sample from this distribution can be generated in the following way. First, we'll pick the number C, which is the number of xi that will report this random coin flip. So we know that so among all the elements which are different from not the first element, we'll pick all those randomly that will report the random coin flip instead of their true value. And this number is because each of those is reported. This Bernoulli is reported with probability 2 over e to the epsilon plus 1. This number will be distributed according to the binomial distribution with this bias and n-1 draws. Now, having picked the C, we'll pick A according to the binomial distribution with bias 1/2 with C. We'll just pick the number of xi's that will report 1. So we know that there are now we have chosen now we have committed to C of the coins reporting this random coin flip. Now we are picking the number of those that will actually report 1. And we'll also pick the number of T will be the number of, again, the elements which are different from the first element that do not report the Bernoulli, the ones which will report their true value. This T is is the number of those that will report 1 condition on the number on the choice of C. So because we already committed that C of them will be reporting, so some random subset of the size C will be reporting on their true value, and the total number of ones reported will denote this random variable as T. What's interesting about these 3 values, they're all all these random choices are completely independent of the data set X or X prime. So we haven't used the value of the first element. Now, what we can observe is that the number of ones in the shuffled output of R of the first data set can be described in the following way. It's the same distribution as the Bernoulli coin flip with with bias 1 over e to the epsilon 0 plus 1, which is the one. This is basically the reporting of the first element, which we know is equal to 1 with this probability, because the original value is 0 for the dataset X, plus A. This is the number of ones coming from those elements that are reporting this random coin flip, plus T, which is the number of ones among the elements that are not reporting the random coin flip. So this is the sum of these 3 random variables is the number of ones is distributed the same way as the number of ones in the shuffled output of the R of X. And similarly for when we shuffle R of X prime, we'll get Bernoulli with because we're reporting 1 instead of 0 as the first element, we'll get a different bias, e to the epsilon 0 divided by e to the epsilon 0 plus 1, and plus the same 2 values again. These 2 are independent of the data set. So now, in order to basically understand the divergence, the privacy guarantee, all we need is to understand the divergence of these 2 distributions over these distributions of these 2 random variables. And to understand why this divergence is small, it actually suffices to notice that this random variable A is chosen from the basically it's a sum of C coin flips, completely random coin flips. So it's basically equivalent to so-called binomial noise. It's noise which is just binomial with random coin flips, and the number of coins which is added is C, which we know its expectation is roughly n over e to the epsilon 0, because again this is the number of coins and this is the bias, and it's very strongly concentrated around this this expectation. So we can, for simplicity, think of this mechanism as adding roughly n over e to the epsilon random coin flips to the output value. So now, question? Yes.
Thank you. Sorry, interruption. So I didn't get how the reporting of true bit is in that schema.
So let's see. So
say where is it?
Yeah. So this is the first Bernoulli. You see in this expression there is this Bernoulli. You see Bernoulli. This one has different bias. In the first expression, when we shuffle the first one, we report the correct we will report 1 with probability 1 divided by e to the epsilon naught plus 1, because the correct value is 0. So and in the second one, the numerator is actually e to the epsilon 0 naught. So it's a higher probability of reporting 1. So the difference between these 2 is just the bias in this Bernoulli random variable.
Yeah, but the question, so how the original bit like xi come into the play?
X1, you mean? So in this case,
X1,
yeah. So this is how it plays, is that that in the first distribution, the distribution is the same as Bernoulli with this bias plus these 2 random variables, and second one is Bernoulli with a different bias, because it's the first bit is randomized, and with some probability it will be 1, and that probability is different in these 2 cases. And this is exactly so in the first one it's this lower probability, and the second one it's this higher probability. So these are just 2. We're defining just 2 distributions, and they differ only with using this.
Okay, thank you.
Okay.
Vitaly, maybe just a quick additional question. So
yes.
the T doesn't it depend on the data set? So it doesn't depend on X1, but it depends on the
no. So T, so basically so far everything we have, these CAT are only conditions on the elements other than the first element. So the C chooses among those who only the elements from the second to the last, which ones will report Bernoulli. And then if once you decided which ones, not which ones, once you decide just on the number of those which will report the random coin flips, that conditions the distribution on the reporting on these elements from 2 to n, and we will just pick T from this conditional distribution. Again, all of these CAT don't even refer to the first element. We're just we're just making some choices about what will the elements from 2 to n do.
Right. But I guess my question was: is T depending on X and X, big X and big X prime, right? So
no. So yeah, no. As I mentioned, no. We are by definition it does not, and all one needs to verify is that indeed, after shuffling, that's the distributions that we're getting. So the distribution is what happens to the first element plus what happens to the ones coming from the other elements that report a random coin flip and other elements that do not report the random coin flips. But these are T is just conditioning and values on the other elements, on the elements other than the first element. So there is no dependence. It may take a little bit. I shouldn't be suggesting that it's completely obvious. It take maybe a bit of thought and maybe best done offline. But it's not hard to see that we're just deciding what the elements are. Other elements, how will they flip a random coin or not? And once we made this decision, everything else is basically their distributions on their numbers are independent of what the first element does. So anyway, so what I wanted to say is that this is equivalent to, in some sense, adding binomial random noise. The number of random coin flips is itself a random variable C, but its expectation is roughly n over e to the epsilon 0. So we can, for simplicity, just assume that that's how many random coin flips we're adding. And it's actually well known that addition of this binomial noise gives differential privacy. And in fact, this binomial noise behave roughly in the same way as addition of Gaussian noise with the same variance. So in particular, if we look at the divergence between the binomial distribution with this kind of where the number of flips is n over e to the epsilon and the same binomial but plus 1, then these two distributions are e to the epsilon 0 over 2 times the square root log 1 over delta divided by square root n delta close. And again, in this case, e to the epsilon 0 over 2 divided by square root n comes just from the variance of this binomial distribution. So if we shift these binomials by 1, we already get this differential privacy. This is not quite the bound we want, but also this is the divergence into distribution where which differ by 1. But actually, in our case, the first element reports true value only with some probability e to the epsilon 0 minus 1 divided by e to the epsilon 0 plus 1. So basically, we don't really need divergence with plus 1. We just have a slightly different bias in the first coin flip. So basically, the one way to think about it is that the first element reports its true value with probability roughly 1 minus e to the epsilon 0. So that kind of amplifies the privacy guarantees a little bit further. So and gives this bound of 1 minus e to the epsilon 0 times e to the epsilon 0 over 2 times the log delta, basically the bound that we claim for randomized response. Anyway, that's the warm up. That's basically the proof of the binary, essentially the proof of the randomized response. there is a bit more calculation, but that's the spirit of the proof. Now let me go to the general result, and first let me state a little bit more specifically what we prove. What do I mean by reducing it to divergence between two specific or explicit distributions? So the result in our work can be stated in the following way. So again, for any adaptive sequence of epsilon not local randomizers, A1 through AN and dataset X, we define a shuffle of X, and as before, like this is just we shuffle the inputs and then apply the sequence of local randomizers in an adaptive way. Then the privacy guarantees that we show for these algorithms are upper bounded by divergence between distributions on pairs of integers. And the first, maybe actually it's easier to explain. The second element, the second value in the pair is C, where C is the binomial distribution with n-1 flips and bias 1 over e to the epsilon naught, which is pretty much exactly the same as the one we just saw. And the first element in this pair is the sum of this binomial noise with random coin flips with C values, again, as we saw, plus Bernoulli, basically the same distribution as we just saw. The first value is this Bernoulli 1 plus e to the epsilon plus 1 plus binomial and C. And the second one is the same distribution, but the bias we're changing the bias as before from Bernoulli 1 over e to the epsilon naught plus 1 to its complement e to the epsilon naught divided by e to the epsilon naught plus 1. So for whatever notion of divergence, in fact, for whatever notions of divergence that is close to post-processing, whatever bound one can get on the divergence of these two distributions, one will get this bound as a guarantee for the privacy for this algorithm, for this shuffled output. And as I've just mentioned, for basically the distribution I've just analyzed is essentially the same. So in particular, one gets this tight bound on the divergence that I have claimed for the general result. Okay, let me now go to the proof on how we prove this more general result. And for this, I'll need a very simple, or I would say a relatively simple observation of the composition of a local randomizer, which is based, first of all, we'll have to review quickly the definition of the epsilon not low LDP randomizer. And the definition is the following: is something is epsilon 0 local randomizer if for any pair of inputs and any output value, especially we'll assume that the output domain is discrete, the probability of that output under these two distributions, the ratio of these probabilities is always at least 1 over e to the epsilon naught. That's essentially the definition of local randomizer. And what this definition implies most immediately is that the output of A on X prime, on this one of these two elements, can be seen as the following way. First, with probability 1 over e to the epsilon naught, we will actually run A on the other input, A of X, and output A of X. And otherwise, well, so with this probability, we'll output this value. Otherwise, we'll output some other distribution. So that so basically, because the densities, the ratio of densities at any point is lower bounded by this 1 over e to the epsilon 0, any element can, with probability 1 over e to the epsilon 0, pretend to be any other element. Basically, it can pretend to be a clone of an output on a different element in the data set from that randomizer. And with the remaining probability, it will be some other random variable, which will depend on these two outputs, but it doesn't matter. What's important is that with some probability, it can pretend to be a completely different element. So taking this one step further, the same decomposition, one can also say that for any, if we take 3 elements, one of them will refer to xi, it's just some element in the data set, and the 2 of them will be x1 and x1 prime, the 2 different elements. Then when we output xi, we can pretend with probability of 1 over 2 to the epsilon 0 to be the output on the first element, x1, with probability another 1 over 2 to the epsilon 0 to be output on x prime, and then we'll and with remaining probability be some kind of leftover probability, some other random variable. It's not so important which one. And this step we just get by basically just randomizing it, pretending with probability 1/2 to be one element and probability 1/2 to be another element. Any element can pretend to be one of the two elements with some probability and be some leftover with the remaining probability. Hope that this decomposition makes sense. Basically, it means that any element can kind of pretend to be one of the first two elements in the data set. Now let's go to the proof itself. So we'll take x and x prime to be two data sets which differ in for simplicity in the first element. We can always assume that they differ in the first element because we're shuffling them anyway, the inputs. Now we'll be describing a somewhat different way to generate the output distribution from shuffling. So in the following, they will generate in the following way. First, we'll pick C as before as the number of elements that are not the first element, this for other elements with indices larger than 2, that will not report the leftover. They will pretend to be either the first or the one of these first two elements. And this number is distributed as a binomial of 1/e to the epsilon naught, just because that's the probability that we have of reporting the not reporting the leftover. Then we'll pick A from the binomial with this C, the number of xi that will report that they're the first element in the first data set. Now, having chosen C and A, these again, C and A are completely independent of the data set, just two random variables. We have just committed to how the elements will behave. We can, what I'm claiming is that the output of the shuffling on the data set can be seen as the following process. First, we'll pick A plus 1 because so we know that A elements will be reporting as x1, and in the data set X, there is also the x1 itself. So we'll have a total A plus 1 elements which will be reporting as x1. C minus A will be reporting as x1 prime. This is this is the other ones, and C. Actually, n minus 1 minus C will be reporting left. There's a small typo here. N minus C minus 1 reporting as leftover, and we'll pick which randomizers are reporting which of those elements randomly and uniformly, because we're shuffling all the inputs. And now, when for elements which we chose that chose to report this leftover probability, we also need to choose because the leftover probability also depends on the element from which the leftover is coming. We'll pick those randomly and uniformly from all the set of values x2 through xn. Again, those, because of the shuffling, we have complete symmetry and all condition on these values. This will be the uniform distribution over these elements that, again, does not depend on the data set. And very similarly, if we look at the shuffling of the output of the x prime, it can be described in exactly the same way. But now A elements will be reporting, pretending to be x1. C minus A plus 1 elements will be one more reporting as x1 prime. And again, n minus C minus 1, it's the same typo, will be reporting this as leftover probability, leftover random variable. So basically, what we can see that once you pick how many of each of the elements, x1, and how many of the elements are reporting as x1 prime, the rest is completely data independent, data set independent post-processing. To be more specific, it does depend on the data set, but that does not depend on which of these two specific data sets we're using. I mean, this post-processing does depend on the values of x2 through xn, and does depend on x1 and x1 prime, but does not depend on which of the data set. So basically what we get is once you choose these values, random variables A and C, when we know these the values in this pair of values, the rest is post-processing. And because privacy guarantees are preserved under post-processing, we get that basically it suffices to evaluate the divergence of these two distributions. And these are exactly the two distributions we have just analyzed. These are just the C is chosen from binomial of 1 over e to the epsilon naught and n minus 1 flips. And we are looking at the divergence in this pair where we output C and also binomial plus 1. And divergence between those two is already gives us bound, which is correct when epsilon naught is greater than 1. We actually don't, because we're in this analysis, we're truthfully reporting the value of the element, the first element. We don't get the correct behavior for when epsilon naught is less than 1, but this can be done very relatively easily using additional lemma. Basically, a result by Kairouz and Owen Vishwanath basically shows that one can view the sort of the output of a local differentially private local randomizers on any arbitrary pair of outputs as the post-processing of basically binary randomized response on some pair of random variables, and the post-processing uses some pair of random variables. In the interest of time, I won't describe it exactly, but basically it allows us to do this, to get the same trick where we basically can think of the first element as reporting the true value with probability e to the epsilon minus 1 divided by e to the epsilon naught plus 1, and reporting a random coin flip otherwise, which gives us the same kind of amplification of privacy, and the rest of the argument is done with these two random variables instead of the outputs of the algorithms. This is again, it's just an additional simple trick. Already the result until now gives us the correct dependence for epsilon when epsilon naught is greater than 1, which is kind of the main regime of interest for us. So it's a little quick. I guess it might be easier to go over it this offline or check the details in the paper, but that's all that I wanted to say about the proof. Let me go to conclusions. First of all, you can find the paper and all the details on arXiv, and we actually have just updated it to include some of the results and better presentations. And if you are checking it, you should check it later today, maybe or tomorrow morning. The code to generate the numerical evaluations is available on GitHub. And let me briefly mention what else we can find in the paper. So as I already said before, there is a more general results that can exploit additional structure and get better amplification results. And we apply it to k-randomized response and get better bounds for it. We have generalization to epsilon 0 delta 0 LDP with essentially no loss. We show how these results can be applied to get sort of the first analysis of TP-HGD, which applies to shuffled inputs, whereas typically TP-HGD is analyzed only for sampling with replacement, because we didn't have good analysis for shuffling. There's also an application to frequency and distribution estimation in the shuffle model. It basically shows that you can take any sort of arbitrary state-of-the-art algorithm for these problems that works in the local model, shuffle it, and get basically performance which is also optimal for, or nearly optimal for, the central model as well. And finally, there is quite a bit more numerical evaluations, which I hope you'll find useful and show sort of the various other regimes of the bounds. And very briefly, I'll mention some potential future work. One is that we still have a constant gap between the lower bound for the binary randomized response and the upper bound. Those would be very nice to close, both from practical point of view and also kind of interesting to understand whether we can tighten the bound. And also it would be nice to get better sort of tight closed form bounds for Renyi differential privacy guarantees. There has been some work on this already. There are some Renyi bounds in the Erlingsson et al. And also in the follow-up work that I mentioned, but so far the bounds are not tight, and we'll hopefully close those soon. Thank you very much for your attention, and please let me know if you have any questions.
Thanks a lot, Vitaly, for the nice talk. Yeah, I think we can take a few questions if there are additional questions in the audience. I can start with maybe a comment. It's nice to see that you have code online. I remember when I first looked at the paper, I don't think there was a code, and I think the numerical bounds, which are tighter and quite nice to use in practice. Okay, they require a bit of care, probably in implementing them.
Right. I mean, yeah. So in the end, we do evaluate the diversity into distribution. The distributions are on n elements, or actually on pairs of n elements, and kind of doing it very fast requires a bit of if you want to make sure it's efficient, it requires a bit of care. We actually describe this, and I think already we described in the first version how to do it. But yeah, it requires some effort. Now we have the code already for the epsilon delta out. We will put the code for an EDP a bit later. Something hasn't gone through all the approval processes yet.
That's nice.
I see there is a question from.
Oh, yes.
Yeah, from Burak.
Yes. So actually, like, I was wondering if this like proof is still like on binary. For example, like, can you go back to the like when we choose CAT on the slides?
You wanna go to the binary?
Yeah.
Okay.
I think like the next part, not the warm-up part, but the actual proof. So basically, while we're choosing CNA, so here, for example, like in the first line, we basically decide like how many like agents will lie, right?
Yeah.
So,
yes. How many agents will be creating clones? We call them clones. They behave as if they're the first or the second element randomly. The goal of this, what we're showing, is that we can view all the other elements as hiding, or creating some kind of noise or additional clones. Basically, their goal is to create lots of clones of the first element, which we don't know which one of those. So yeah, these are the ones. C is those which will be pretending to be clones of the first element, or one of the first two elements.
So yes, on the basically like on the second line, we will choose between like xi and
yes,
x1 and x1 prime, right?
Yes,
so
yes.
Basically,
right.
I mean, do we know like what is the alternative to the? Because I mean, if this is not binary, so there are like many options for x1 prime, right? So what's x1 prime here?
So we start by fixing two data sets. So the analysis of differential privacy, it suffices to show for any two data sets, the divergence that you get between the resulting distribution is bounded. So now all we need, at this point, we can just fix the two data sets. We don't, and these two data sets only have two possible values for the first element, and of course the rest of the elements are the same. So at this point, our post-processing and all these definitions are fixed with respect to this specific pair, and we prove bounds on the divergence in the resulting pair of distributions. That's again, that's sufficient to get a general bound. So all these, maybe it's worth pointing out, this all these post-processing and kind of this cloning, it's all, I mean, it's not what algorithm does. It's kind of just, we do it only for the purposes of the analysis. We're thinking of this as a purpose. Now, we're not thinking of actual elements lying that they're something. This is we analyze it as for a specific pair of distribution. Otherwise, of course, the element xi doesn't even know what x1 is or x1 not. Like it's, I mean, just like this is not how the algorithm is run. It's just a analysis. For the purposes of the analysis, we're thinking of these algorithms as creating these clones, and hope that that is what you meant, but if not, please clarify your question.
Okay, maybe I have a question which is a bit related.
Thanks.
Oh, sorry. A bit related to this. Maybe, in fact, my question is about a little bit the relation to this previous work, this blanket work, right? Which was also using a decomposition of the local randomizers, but a different one, right? So it was essentially separating the part that depends on the input and the part that doesn't depend on the input, and then using the part that is independent from the input as kind of the source of randomness that provides the amplification.
Right.
So here you're using a different composition. So just, okay, it's not completely clear to me if this decomposition now allows you to extract or to account for maybe more randomness, or it allows you to more easily quantify the effect of this randomness in the end, because you end up with just divergences between binomial distributions, which is nice. So just a bit of intuition on that.
So where does this, so first of all, maybe, yeah, it's a decomposition into what was called a privacy blanket, was used in the paper of Bal and others, where basically they decompose each output into part which is completely, basically in some sense, shared between all the outputs. It's kind of input independent, and they call it blanket, and the other part which is input dependent. And this kind of, because we have, we're basically sampling from that blanket with some probability, that blanket kind of creates enough of you could say noise, or at least uncertainty in the distribution of each of the elements. The difference here is that we are decomposing in a much more sort of, in a way which is specific to a pair of datasets. Whether it's, I mean, the analysis technique is also different, so it's a little bit hard for me to say that there. It's also, you really have to use the fact that all the randomizers are the same, and kind of because you'll be trying to create uncertainty in the output probability of each of the element. It's a little hard for me to say exactly why the previous technique does not get the right dependence, the tight dependence. It's I mean, there is one a little bit. I don't think I can. I mean, I have a hypothesis why exactly that happens. Like, but it's not. I don't have something that I can easily explain and be sure that it's correct. It's basically a different analysis in several ways. Even though, yes, the composition, a different decomposition also plays a role, and it's kind of a useful trick to think of these outputs as potentially pretending to be one thing. Okay, that case is not pretending; it's just different, as outputting two different random variables. One is data independent ones.
I guess these decompositions can have larger, more general applications, maybe in a way. So I guess that's also a bit why I'm asking the question. But I understand it's a bit difficult. Indeed, your decomposition really depends on on the two data sets. So essentially, is really decomposed according to the two elements that differ, which is not at all the case in the other decomposition. Okay, thanks a lot. Do we have more questions? Doesn't look like it. All right, I think we will stop here. Thanks a lot again, Vitaly, for the nice talk. And I think this now provides a great opportunity for me to look into the details of the analysis.
Thank you all, and feel free to send me an email if you have any follow-up questions. And as I said, also please take a look at the paper. Should be a better updated version will be up by tomorrow.
All right, thanks a lot.
Thank you.